of epsilon. So omega is v times 0, 1. So here we use the appropriate rescaling and obtain, of course, that z is from 0 to 1. Okay, so the new unknown function is the following: omega epsilon of xz is omega without the epsilon, x, big Z. Okay, so the equation for the heat equation basically becomes a bit more complicated. Of course, when you do this change of variables, so it's a bit nasty. So equation 5 becomes, I'll write it down. Just usually I don't write if the equation is 2 pages long, but this is not so which is very usual if you want to compute something. So minus kappa h squared plus s x theta. So this is a small x minus 2 kappa over epsilon squared so you can see the difference between big and small x minus kappa over epsilon to the 4th h squared. So of course the if you have epsilon to the squared, this would appear in the second order corrector. To the 4th, it would probably here in this case appear in the first order. So actually at the 0th order approximation plus 2 kappa over epsilon squared Okay, so it's a lot of derivatives and a lot of terms with h. So kappa h Laplace. This is so that you get a bit of a sense of what we are looking at. So what usually happens in these equations, you get a lot of terms, but usually the zero order approximation takes place at a very simple equation when you plug in the asymptotic approximation, and then all the other terms that appear later in the first, second order corrector, etc., are basically already known. So it's not that you are working with them at the same order, so it's not so problematic. So minus kappa h squared z squared okay, and now it's almost over. So 1 over epsilon squared h squared u 0 Okay, from a very simple equation, which is basically linearized, so it's even simpler, you get this bit of a nasty equation. But since you're doing this rescaling, of course, it gets more or less easy to handle. So let me just comment that let's denote this by 7. So in 7, we use So the following notation, gradient of h depending on x and big X is epsilon's gradient of x, h1 of x, plus gradient of big X, h2 of x. Just let me check that here we don't have epsilon squared, I'm not sure. Yeah, it's okay. Okay, so Laplace of h epsilon Laplace x h1 of x okay, so this is what you're working with. So in order to obtain some roughness effects, usually in problems with the heat equation, you noticed the last time that you have to go to even the third order corrector or even more, and then from the compatibility conditions you obtain some equations, some simple ODEs for the zero order approximation, first order corrector, and usually the first order corrector carries the effects you want, maybe sometimes the second order corrector, so you have to compute a lot. But here, since we have this specific profile, basically at the zero order approximation for very specific alpha, you obtain the effect that you are searching for. So you have the asymptotic expansion for the temperature. Theta, so you have theta of x, big X, z, is theta 0 of x, big X, z, okay. So again, you plug this into the rescaled system of equations. And what do you obtain? So the main result, you have to do a bit of computation. It's written in the paper. I will not go through it. So in the context, in the critical case, so if you take alpha, I don't remember what exactly alpha did we take in the last paper. I think it was around order epsilon. So here you take alpha to be order 1 over epsilon. So in the boundary condition, (6)(1). So you obtain the effects of the rough boundary. Of course, it's easy when I write it down, but you have to, it takes a lot of work just to know what kind of profile you want to look at, and how do you correspond the parameters to that. Does it have physical justification or not, etc. So theta 0 of xz is given in this form. So gamma h1 of x, that should th minus tb. So gamma is, I think I didn't write it down. Let me just, it is given from, due to the rescaling of alpha, I think, just a second. Okay. So here you have, we can have gamma is epsilon alpha, which is of order 1. Okay. Okay, so Down you have k e to the m over 2 plus gamma h1 of integral of 0 to 1 e to the m c squared over 2. So it's not a very complicated expression, but it has some effects that you are searching for. So this k, we mentioned that it carries some effects of the rough boundary, and you also have this m, which is, this can be derived, you can check in the paper. It's given as the integral of the two-dimensional torus, gradient of x h2 dx. So you have the effects of h2, of the boundary rugosity, in m, in some sense, and this m appears here. So okay, I can write this down here. So gamma is epsilon alpha, which is of order 1, and xz are from gamma. Okay, so here you have the effect of the rough boundary. Okay. However, of course, you need to say, okay, it took a very specific alpha, but what happens if alpha is, as before, as we mentioned, if alpha is much bigger or much less than 1 over epsilon? So I have a couple of remarks. So remark 1. So if alpha is much less than the order of 1 over epsilon, then you have theta 0 of xz. It's easy to show that it's just equal to tb. So this means that the process is dominated by the prescribed temperature on the bottom part. Okay, and the other case, when alpha is much bigger than 1 over epsilon, you will have some effects of the rough boundary, but they will be dominated by the external temperature. So let's write here theta 0 of xz. So you have th minus tb over, so you don't have this parameter k, which also carries some effects of the rugosity, but I didn't explicitly write it down. So you have this term, c squared over 2 Okay, so in this case, I can write down there. So some effects of the roughness. But the process is dominated by the external temperature. And this is given by TH. Okay, one more remark regarding this. If that m, which was that torus integral that you obtain, if it is equal to 0, which basically means that H2 is 0, this means that you have no effect of the rough boundary. And you have a linear function by z. Okay, so let me just wrap this up. We have here, if you want to go a little deeper, a lot of computation to do, but I think it's more important to show these results in general, as this course is more of an overview of the different areas in this asymptotic model in fluid mechanics. So, okay. So in case of the domain of the following form, so h epsilon of x is epsilon h1 of x plus epsilon squared h2 of x over epsilon beta, where beta is less than 1. No So we took a very specific beta to be equal to 2. However, if you take this to be less than 1, no roughness-induced effects can be found in theta 0. And finally, if you would, in this paper you don't have the justification of the model, maybe in some later paper, I'm not sure. But if you want to do justification of the model, you can go by the two-scale convergence method, or the more classical one that we are using, so the error estimates in suitable norms, so rigorous justification. So error estimates in suitable norms. So this would be, of course, better after you would compute, for example, theta 1 and theta 2, and see if you can justify the usage of the correctors by improving the overall error estimate between the original solution and your computed approximation. Okay, so that was what I wanted to talk about today. We will continue in 2 weeks. I don't know if I will continue maybe two or three more lectures regarding non-isothermal flows, and then depending on if Professor Pajani will speak something, or we will see, I would like to talk something about the system of thin pipes. So this is the idea. Thank you for your attention.